Section 2.5 is limits at infinity. So here we are determining what happens at the left and right edges of the graph, if we were looking at a graph. So let's consider the function tangent inverse of x, whose domain is negative infinity to infinity. And as x becomes arbitrarily large, which we denote by saying x approaches infinity, we see that the graph itself, f of x, approaches pi over 2. So as we move out, as x approaches infinity, so we're going to put our pin on the graph, and we're going to make our pin travel towards infinity, but we cannot pick our pin up off the graph. So in other words, we got to keep our pin on the graph, and the graph will guide us where to go, right? So I'm going to put my pin somewhere on the graph, and I am going to travel towards infinity, but I can't pick my pin up off the graph, and what I see is that this graph ends up approaching a y value of pi over 2, which is why we say that the limit of f of x as x approaches infinity is pi over 2. We can say something similar or do something similar if we approach negative infinity, which means we want to see what the graph is doing at the far left side of the picture. So I put my pin somewhere on the graph and I move towards negative infinity, so move towards an x value of negative infinity, and what we see is that our graph slowly collapses to negative pi over 2, or has a y value of negative pi over 2. Anytime you find the limits at infinity, you have the opportunity or the chance that you might discover a horizontal asymptote. We need to be very careful with this. Just because you're finding a limit at infinity does not mean that your answer is a horizontal asymptote. However, if you're finding a limit at infinity and the answer is numerical, then yes, it is a horizontal asymptote. So in other words, since that says pi over 2 rather than saying an answer of, say, negative infinity, then we know that this is a horizontal asymptote. If your answer is a number and not a symbol, then it's a horizontal asymptote. But that is only happening if you're finding limits at infinity. All right, and so we actually have the definition. If f of x becomes arbitrarily close to a finite number, so L, for all sufficiently large and positive x values, then we would write the limit of f of x as x approaches infinity equals L. We can do the same thing with negative infinity. In this case, we would say that's approaching a different value, which we've labeled M. And so what we want to do now is figure out a way to evaluate these limits, but we want to eventually attempt to do it algebraically. Right now, all we have available to us is a graph, and since we don't have a graphing calculator, and it's just cumbersome anyway, we don't want to have to graph a function every time we want to find the limit at infinity. So let's do one more where we're looking at the graph, and then we'll talk about how to handle these algebraically. So here we've got the graph of 2 plus 10 divided by x squared. And we can, again, look at the graph and say, okay, we want to find the limit at negative infinity. So that says we want to see what the graph is doing at the far left edge, right? So I put my pin somewhere on the graph, and I can't pick my pin up off the graph, but as I move towards negative infinity, what y value does my graph appear to approach? And it appears to approach y equals 2. So here, put my pen on the left side of the graph, and as I try to move towards negative infinity, the y value that my graph appears to approach is this red dashed line, which is the line y equals 2. So we say that the limit as x approaches negative infinity, right? Limit of f of x as x approaches negative infinity is 2. Since this answer was a number and not a symbol like infinity or negative infinity, since the answer is a number, then we know that we are looking at a horizontal asymptote. It is possible for a limit to be both an infinite limit and a limit at infinity. Remember that an infinite limit means that the answer has infinity in it, either positive infinity or negative infinity, and limit at infinity describes what the x value is approaching. So as you move to the left or right, as you move to the far left of the graph or the far right of the graph, you'll find that the ends of the graph are heading off to infinity. And here's an example of an infinite limit at infinity. So as we move towards the right side of the graph, we see that the graph itself is moving upward, right? So as x approaches infinity, the y value is also approaching infinity. So as we move to the right, the graph itself is moving upward. If we move to the left, eventually we see that the graph itself is moving downward. Now this graph could be pointed up like this, and we could say it's being moved upward, whatever. The point is that as you move to the edges of the graph, the ends of the graph are shooting off to infinity or negative infinity. So this is an infinite limit because the answer says infinity or has infinity in it. So it's an infinite limit at infinity. Right, so since the answer says infinity, it's an infinite limit, and then this infinity says it's at infinity. These all are infinite limits at infinity because they have infinity in their answer, and then their x values approaching infinity, either positive or negative. All right, so we have a theorem that allows us to get to some of these answers a little bit more quickly without having to look at a graph. And we're told let n be a positive integer and let p be the polynomial. P of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, so forth and so on until you get to a sub 0. Then the following statements hold. Really, this is just a polynomial of degree n, and each term it could be one less. Right? The only stipulation is that this first term does not have a coefficient of 0. All right. Then the limit of x to the n is infinity. If n is even, that should make sense. Regardless of putting a positive infinity or negative, a positive number or a negative number, regardless of if you evaluate at a positive number or a negative number, if you raise it to an even power, the answer is always going to be a positive answer. If you have an odd power, right, then the limit at infinity of x to the odd power returns infinity, but the limit at x, as x approaches negative infinity of an odd power, will return a negative answer. This one is probably the most significant to us. If you have 1 divided by x to the n and you try to evaluate at infinity or negative infinity, the answer should be 0. What's happening here is you can think of this as, say, $1 bill, right? You have $1, and when you evaluate it at infinity, so you plug an infinity in for x, now you've got $1 divided by infinity's a big number, so let's just think everybody at Blinn College, right? So you have $1 divided by everybody at Blinn College. Well, Blinn College has like 18,000 students, so 1 divided by 18,000, how much money are you going to get? Nothing, right? And so that's that's what we're seeing here. If you have, and in fact, it didn't have to be 1. It could be $100. If you have $100 divided by everybody in Texas, right? Because that's a pretty big number. $100 divided by infinity, still you're not getting any money, right? So no matter what the numerical, as long as it's a number, right? No matter what the numerator is, as long as it's a number, divided by something that's approaching infinity, you're going to get 0 as an answer. All right, and then the polynomial itself, the limit at infinity or negative infinity of a polynomial, as described up here, is either infinity or negative infinity, depending on the degree of the polynomial and the sign of the leading coefficient. So really what's happening is we can get a lot of our information based on what the limit of a polynomial is off of that first term. All right, so let's evaluate the limits as x approaches infinity and negative infinity. So the limit of 3x to the 4th minus 6x squared plus x minus 10 as x approaches, let's do infinity first. That should be equal to the limit of just that first term. We actually know that the 3 can come out, so we don't really have to worry about the 3 other than if it were negative, we would have to retain that sign. We know that infinity raised to the 4th power, it's an even power, so it's going to return a positive answer. So we're going to have 3 times a positive big number. Well, 3 times something very big and positive returns a positive infinity. The limit of 3x to the 4th minus 6x squared plus x minus 10 as x approaches negative infinity. Again, we really just need to consider that first term. Negative infinity evaluated at an even exponent should return a positive value, so it's going to be positive. So we're going to have 3 times a very large positive number, which should again return infinity. All right, so what we're describing here is the end behavior. What we're saying is the graph of this function on the right side, right, so as we approach the far right of the graph, our graph should be going upward. So we know that the right side of this graph is pointed upward. Let's go to the left side. So the far left of the graph, negative infinity, right, should also be pointed upward. So this is what we know. And we really don't have any idea what's going on between this end of the graph and this end of the graph, right? We know they need to be connected, but we don't know if there's bumps in the graph or what's going on. So we're not really sure what's going on in the middle just yet, but we do know what the ends of the graph look like. Okay. In behavior of polynomials, the example was often, or the behavior of polynomials rather, as x approaches infinity and negative infinity is what is often called end behavior. And what we want to figure out now is we've done it for a polynomial, but we want to figure out what it looks like for rational functions. Remember, those are the ones that are a polynomial over a polynomial. For algebraic functions, like perhaps the square root of something, and transcendental functions, sine of x, or we're not quite there yet, so e to the x, something like that. All right, an effective approach for evaluating limits of rational functions, so it has to be a rational function, is to divide both the numerator and the denominator by x to the n, where n is the largest power appearing in the denominator. All right, so it's just a little trick to try to reduce this to something that we can quickly evaluate. A lot of students get annoyed by it because there are a lot of steps to show without a whole lot of benefit until you get to the very end. So a lot of students really get grumpy about this. You have to show all the steps. All right, so let's determine the end behavior for the following function. Let's do the limit at negative infinity first. And we'll rewrite the function 40x to the fourth plus 4x squared minus 1 over 10x to the fourth plus 8x squared plus 1. Now, you have to show that step. You have to show what you're applying the limit to. You can't jump in and start dividing immediately. I need to see first what you're attempting to take the limit of. Now, the next step is to divide everything by the biggest variable, not the biggest term, the biggest variable in the denominator. The biggest term in the denominator is 10x to the fourth. I don't want to divide by 10x to the fourth. I want to divide by the biggest variable. So in other words, just the x to the fourth. I don't want the 10 with it. Now, what a lot of students fail to see is that with limits, there are really only two things that you can do. You can multiply by the number 1, or you can add the number 0. But you get to decide what your number 1 that you're multiplying by, or what the number 0 that you're adding in look like. Technically, what we're actually doing here is we are multiplying this guy by the number 1, and our number 1 is 1 over x to the fourth divided by 1 over x to the fourth. And this 1 over x to the fourth is getting distributed to each piece. This one's distributing to the guys on top, right? And we're getting this. That part, you're just doing in your head. What I'm wanting to see is this first step, which just states what you're attempting to do, and then this application. Now, what happens here, and I do need to see this step as well, and do not do them all at once. So a lot of times I'll show you what I'm talking about. A lot of students will do the steps, but they do them on top of each other. Well, remember, I'm looking at a piece of paper after the fact. I am not watching you as you do it. So I don't know which step you did first. So unless you write one step per statement, I'm not going to be able to determine if you did this in the correct order. So one step per statement with equal signs in between. All right, so the next thing I want to do is reduce. So x to the fourth will cancel x to the fourth, and I'm left with just 40. These two x's cancel two of those, so you end up with 4 divided by x squared, and nothing cancels in that last one, so it just stays as is. In the denominator, we have 10. These two cancel two of those. What I will see sometimes is students going from this step and in their head doing this. Well, I have no idea what you decided to divide by. You have to show me this middle step. if you just go from here to here, how do I know you didn't look at your neighbor's paper and just write this down? You have to show me every step. Instead of being grumpy about having to do the steps, realize that every time you show me a step, you earn another point. So this should be a free point on your exam that you don't really have to think too much about. All right, at this point we can now evaluate. So I'm going to take the negative infinity and plug it in. There is no there's no x here, so there's no place for the negative infinity to be inserted. But here there is. Negative infinity squared is going to give me a big number. It's going to be positive. So if I have $4 divided by a big number, $4 divided by a big number, I'm not going to get any money. None of us are going to get any money. That approaches 0. And that adheres to number 3 from our theorem 2.6, where we said 1 divided by something raised to a power, as that x is going to either infinity or negative infinity, should take us off to 0. Now again, our theorem says 1, but it actually holds true for any number, because we could factor a 4 out and would leave us with just a 1 here, and then it should work. All right, this should also, 1 divided by infinity, right, because a negative infinity to the 4th power returns a large positive value. That should shoot off to 0. No place to evaluate the negative infinity for here, so it just stays as 10. $8 divided by a huge amount, nobody's getting anything. Same thing here. So now we come back and we say, okay, we have evaluated. We've actually taken the negative infinity and plugged it in. Once you do this evaluation, you stop writing limit, and so now you just have 40 divided by 10, which is 4. Things I'm looking for. I'm looking for this step, this step, this step, this step. I don't care if you say 40 divided by 10 in your head and give me just the 4, that's fine. I'm looking for limits. I'm looking for equal signs. I'm looking for you not writing a limit in either of these because you've actually done the evaluation. Now, here's one thing I will do. If you have done the limit at either negative infinity or positive infinity, it doesn't matter, and you're asked to find the other one, then start off the problem. It's the same process, so I'm okay at this point with you, since you've already done it once up here, you can rewrite this if you want, but since you've already done it once, I'm okay with you skipping that step and moving to this one. But you have to have shown this step at least once somewhere on the page for this particular problem. When in doubt, show your work. Okay, now we evaluate. So this goes to 0, this goes to 0, this goes to 0, this goes to 0, and we get 40 divided by 10, which is 4. So these were limits at infinity. Did they give us a horizontal asymptote as their answer? Because this is numeric, the answer is yes, right? This is a number, it's 4, and in fact, if you look at the graph, you can actually see that this graph right here tapers off, and at the edges, right, approaches a y value of 4. Remember that for horizontal asymptotes, your graph, at least locally, and this graph doesn't do it, but for horizontal asymptotes, you actually can cross the horizontal asymptote. In fact, you can cross it several times, but at the edges of the graph, it should settle down and approach the value of the horizontal asymptote. Okay, let's do this one as well. we have the limit of 2x squared plus 6x minus 2 divided by x plus 1. As x approaches negative infinity, right? So first thing we want to do is divide by the biggest variable in the denominator, not the biggest variable in the problem. A lot of students make that mistake. The biggest variable in the problem is x squared. We don't care. We want to divide by the biggest variable in the denominator. So we are dividing everything by x. All right, let's reduce. A lot of students right here, they'll cancel those and then won't write anything down. X divided by x is 1. A lot of students will just do this. They'll say it's 0. No, it's not. Anything divided by itself is 1, right? So we got to make sure that we write that down. Now we evaluate. So 2 times infinity is going to give us a very large number. 6, there's no place to plug the infinity in, so it just stays 6. 2 divided by something very, very large. That's $2 divided by a whole bunch of people. That's going to shoot off to 0. 1 divided by a bunch of people shoots off to 0. Here we have no place to plug the infinity in. So if we read across, excuse me, we have infinity plus 6 minus 0. Well, infinity plus 6 is just infinity, a little bit bigger infinity, right? Divided by 1 plus 0. Well, infinity divided by 1 is just infinity. All right, so, oh, but it's a negative, isn't it? Oh, I thought, oh, let me go back. I lost my negative sign. Right here. I hate when that happens. Okay. So if I take negative infinity and I plug it in, 2 times negative infinity gives me negative infinity. 2 divided by negative infinity, well, that doesn't matter. That shoots off to 0, so does this one. So we end up with negative infinity plus 6. Very negative number plus some positive stuff still returns a large negative number. Yikes. Okay. So here we now want to do the limit at infinity. So we rewrite the problem. If you want to skip over this step since you've already done it once before on the page, that's fine. Make sure I do this correctly. All right, we're now evaluating at a positive infinity. Infinity plus 6 is just more positive, so positive infinity divided by 1 is infinity. Okay. If we wanted to, we could talk about what this graph looks like. Not sure what's going on in the middle or anything like this, but I know the left side of the graph is doing something like this because the left side and the answer is negative, so it's pointing downward, and the right side of the graph, right side, positive, so it's pointing upward. Now, I don't know what else is going on in between. You know, maybe the graph is doing something like this. I have no idea, but I know that the ends of the graph are correct. No idea what's going on in the middle until I do a little bit more work. Okay. In behavior and asymptotes. So in college algebra, we had this way of describing the horizontal asymptote, and it was based on the degrees. And it said if the degree of the numerator is less than the degree of the denominator, then there's a horizontal asymptote at 0. And again, this is if we were looking at rational functions. And we said if the degree of the numerator was the same as the degree of the denominator, then the horizontal asymptote was the leading coefficient of the numerator divided by the leading coefficient of the denominator. And then we said if the degree of the numerator was exactly 1 more than the degree of the denominator, then we didn't have a horizontal asymptote, we had a slant asymptote, and we kind of moved on from there. Well, we can, using calculus, be more descriptive, and so even though you have a non-calculus way of dealing with these, because you are in a calculus class, I expect you to use calculus. So you can use these little rules to check your answers, but on an exam, I want to see work. Okay, so we've had a couple of sections of limits, and here I want to relate those limits and what the answers are back to the graph. So if the limit is approaching a number, I'm sorry, if the x for the limit, right? So if your x is approaching a number from the left or the right, and your y value is positive or negative infinity. So think about what's happening here. Here we have a specific number. So I'll try to sketch something like this. So here we have a specific number. Let's say it's the number 1. As we approach 1 from the right, if our graph goes off to infinity or negative infinity, so let's say we're approaching 1 from the right and it heads south, then what's happening, so what I've described here is the limit as we approach 1 from the right of this function gives us an answer of negative infinity. Then you are looking at a vertical asymptote. And it only has to be from one side. So if I give you x approaches 1 from the right of f of x equals negative infinity, tell me what that means. All you have to say there is a vertical asymptote of 1. You do not have to have x approaching 1 from the left for this to be considered a vertical asymptote. All right? So from the left or the right, if we get infinity or negative infinity as an answer, then this guy is considered a vertical asymptote. So anytime you have a number, x is approaching a number from the left or the right, and the answer is positive or negative infinity, then you are, you know that you're looking at a vertical asymptote. All right, well, what if you have x is still approaching a number from the left or right, but you receive a numerical answer? Then you possibly have a hole. You have to factor and cancel. If you see that factoring, if you see that you can factor and cancel, then you definitely have a hole in your graph. If you cannot factor and you can't cancel, then there's not a hole and there's really no description you can say here other than there's a point that you can describe the y value that the graph is approaching. If your x is approaching infinity or negative infinity, so now we're looking at the edges of the graph, and you get a numerical answer, then you must have a horizontal asymptote. So let's do something like this. So we could have the graph. So here, the limit as x approaches infinity of f of x is 2. So as we look at the right side of the graph, the y value is 2. And again, your graph could actually do something like this and then taper off. That's completely fine. Wherever it tapers off, and it doesn't have to be below that horizontal asymptote, it could actually drop down towards that horizontal asymptote from above. That's completely fine. The limit at infinity of f of x then is 2, so this describes a horizontal asymptote. If you have the limit at infinity or negative infinity of a function and it returns either infinity or negative infinity as an answer, you have a possible slant asymptote or other asymptotic behavior, or nothing at all. All right, these are just possibilities. So be mindful of these in particular, and don't forget how to determine a hole in the graph as well. Okay, so hopefully you have some general ideas of what your basic parent functions, your basic functions that we often use, general ideas of what they look like. E to the x really should be a graph that you have a general idea of what it looks like. It's an exponential, right, because the variable's in the exponent. So the fact that it has x in the exponent makes it an exponential. E itself is a number, but it's a number that goes on forever. It's 2.87 whatever, goes on forever. Or 2.7818, that's what it is, 2.7818. Anyway, it goes on forever. I always think of it as E is a little less than 3 and pi is a little more than 3. Those kind of help me get those straight in my head. But exponentials always have this sort of banana shape to them. They start off small and get large rather quickly. If you've ever heard someone say, well, rabbits multiply exponentially, what they're saying is that you start off with just 2 rabbits, right? But they very quickly quickly increase to a large number of rabbits. Again, they have this sort of banana shape. Notice that in all of these graphs, now here I started at 2 because we were talking about rabbits, right? And I didn't have a graph over here because how do you have a negative number of rabbits? You don't. But notice that for this graph, notice that it always stays above the x-axis. So if we're describing the end behavior, we would say at the far left of the graph, right, so over here, the graph appears to be approaching 0. So look, we have x is approaching negative infinity or positive infinity, and it gives us a number for the answer. So here we are looking at a horizontal asymptote of y equals 0. Whenever you write asymptotes, they have to be written as equations. So asymptotes will always say y equals 0 or x equals 0 or y equals x plus 2 if you're looking at a slant asymptote, that kind of thing. So always, whenever you are given or whenever you're describing an asymptote, you have to write it as an equation. All right, well, that's the left side of the graph. The right side of the graph, the right side, so positive infinity. What is the right side of the graph doing? Well, as I put my pin on the graph and as I try to move towards an x value of positive infinity, but I can't pick my pin up off the graph steers me towards positive infinity. So here, if I'm trying to evaluate at infinity and it gives me infinity as an answer, from the previous page, I have the possibility of a slant asymptote. Well, generally, we only describe those slant asymptotes when we're talking about rational functions. So here, this, it was a possibility, but it's not happening, right? This is not a rational function. It's a transcendental. Rational, remember, it's a polynomial on top of another polynomial. So p of x over q of x. All right, ln of x. Well, ln of x is the inverse of e to the x. And the reason that's important is because inverses are mirror images of each other across the line y equals x. So here is our e to the x graph, this pink graph, and if we were to fold the paper on this green line right here, it would land on top of our blue ln of x graph. That's because they're inverses, and one of the traits of an inverse is that it's symmetric about the line y equals x. All right, so we're looking at our blue graph here, and we want to describe the limit at, we can't actually describe it at negative infinity, because way over here on the left side of the graph, at negative infinity, right, the blue graph doesn't even exist. This red graph goes on forever, right, but there is no blue graph. This blue graph, in fact, just stops sharply at a vertical line, right, of 0. So here we're going to say the limit as x approaches 0, and we're coming at 0 from the right. There is nothing to the left of 0. So the limit as x approaches 0 from the right of this function. Looks like the graph takes us off to negative infinity. So what we've just described here is a vertical asymptote, right? If our x is approaching a numeric value from the left or the right, and the answer is positive or negative infinity, then we are describing a vertical asymptote. All asymptotes have to be written as equations, so it should be x equals 0. We can describe what happens on the right side. This graph looks like it might taper off, but in fact it doesn't. It does grow, it just grows pretty slowly. Eventually it would get to infinity. If we are looking at the limit at infinity and it returns infinity as an answer, then there's a chance of a slant asymptote, but again that only happens with rational functions, and this is not a rational function, it's one of our transcendentals. Here's another transcendental function, cosine of x. Hopefully you know what the graph of cosine of x looks like. Notice it goes on forever, and if we look at the left side of the graph, we have to say that this thing does not exist. And the reason for that is it just goes on forever and never collapses down, right? It just continues to do the same thing, and it doesn't taper off or anything like that. So it doesn't collapse to a single spot, so that limit at negative infinity doesn't exist. On the right-hand side of the graph, same thing, it goes on forever, and we can't ever get it to taper down to a single spot or settle down, right? So again, we say does not exist. Notice I don't have an equal sign here. The reason is if I put an equal sign here, I'd have to say the limit of cosine of x as x approaches negative infinity does not exist. And there is no sentence in English where we say the words does next to each other. So we would just say the limit of cosine of x as x approaches negative infinity does not exist. Okay, so if you ever wonder why you're not seeing me put an equal sign there, that's why. It's not proper to do so. All right, so here we formally just state what these answers are. The limit at infinity of e to the negative x. What's happening here is e to the negative x can be rewritten. If you have a negative exponent, you can always move that across its own fraction bar, right? And so this becomes, there's an invisible one up here that becomes visible, so it's 1 over e to the x. And then honestly, if we're showing every single step, you should figure out what the limit of 1 is and divide it by the limit of e to the x. Both of these are x is approaching infinity. There is no x value to plug this in, so we just get 1. And now we're looking at the limit as x approaches infinity of e to the x. Well, this limit is infinity, so you end up with this whole piece going to infinity. 1 divided by something very big gives me 0 as its answer. Similarly, we can say this, right? We can do the same thing for this one. So I don't know that they needed to be written, right, because you could actually get there, but here they are formally, and please feel like you can use these, just by memorizing them. All right, let's state the limits required to find the vertical asymptotes of the graph. All right, I'm just asking you to state the limits. I'm not asking you to do anything with them. All right, so I may continue on, right, but state the limits required to find the vertical asymptotes of the graph. So there's a couple of things that we're trying to do here. Let me come off to the side and factor this. I know that I can take a 2 out of each piece in the numerator. In the denominator, let's see, I think that factors. 3x times x would give me 3x squared. And then there's a couple of combinations you could use for 8, 1 and 8, 2 and 4, but not all of them work, right? We would want a positive 4 and a negative 2 to give us the negative 8, and based on where I put them, 3x times 4 gives me a positive 12x, negative 2 times x gives me a negative 2x. When I combine those, it gives me that 10x in the middle, and it's positive. If you need to, you just play around with it until you've factored it correctly. That numerator also factors. I have a couple of choices for 6. It could be 1 and 6, or 2 and 3. I'm going to pick 2 and 3. And so let's see, 3x times 2x would give me 6x squared. For a negative 2, let's do a positive 1 and a negative 2 here. Now, a couple of things guided me on that. First of all, I've done this for years and years, right? So obviously it's going to be a little bit quicker for me than it might be for others. That's okay. I don't care how quick it takes you to do something as long as you can do it. But another thing that guided me is I saw that I had this negative 2 down here and a 3x, right? And since I already had a 3x sitting here, I just thought, well, let me try putting the negative 2, remember, because I'm trying to find two things that multiply together to give you a negative 2. Well, that's either going to be negative 2 and a positive 1 or a negative 1 and a positive 2. I opted for the negative 2 because I already saw that factor down in the denominator and was hoping that these might cancel. Let me make sure this works out. 3x times 1 is 3x. A negative 2 times a 2x gives me negative 4x. That adds up to a negative x, which is what I had in the middle. So yeah, that's the exact factorization. Notice that this guy cancels this one. That cues me in to the fact that I have a hole in this graph. If something cancels, you have a hole at that 0. What I was asked to state, though, were the limits for the vertical asymptotes. Vertical asymptotes come from your denominator equaling 0, provided that a factor doesn't cancel. So I factored all of this out. This is a possible vertical asymptote at x equals 2/3, and a possible vertical asymptote at x equals -4. You just take each piece, set it equal to 0. Now that I see these things cancel, I can erase this guy, because I know that while I thought he might be a vertical asymptote, he's not. Since he cancels, he's actually a hole. So when they ask to state the limits required to find the vertical asymptotes, all they're wanting is the ones for the vertical asymptotes, nothing else. So the limit would be the limit as x approaches -4 from the left and the limit as x approaches -4 from the right, you should do both, of 12x squared minus 2x minus 4 divided by 3x squared plus 10x minus 8. You could even put the, because you've shown the work elsewhere on the page, you could put the factored version here. So this guy, right, reduced to 2 times 2x plus 1 over x plus 4. And then you could go on and do the work if you wanted to. I'm not asking you to. I just wanted you to state the limits. Oftentimes on the exam, I will write this as a multiple choice question. So I might have this guy, one of these guys written out. I might have it completely worked out with the, with the answer even. And, infinity or negative infinity or whatever. But I'm asking you, I would have just a bunch of limits there and would say something like, which of the following is a limit that you would use to find the vertical asymptotes? Or I might have this stuff written out and say, what do you know? So I might have all of this written out, and then let's see. It's going to be a negative on top, negative. So, it might look something like this, right? And so I would have this limit written, and I would say, what can you, tell me what you now know about the graph of f of x. And you would say, well, I now know the graph of f of x has a vertical asymptote at x equals -4. Right? The fact that this is a number being approached from the left or the right, and it gives you an infinity or a negative infinity as its answer, you now know that you have a vertical asymptote there. So I might give you this information and say, what do you know about f of x? Okay. So similarly, state the limits required to find any holes of the graph. Well, we've already done this work. We know that 3x minus 2 is the piece that canceled, so that's where our hole occurs once we set it equal to 0 to determine the number. All right, so we now know that the limit as x approaches 2/3 from the left of, excuse me, this rational function we know that it factors and things cancel, and so we end up with just 2 times 2x plus 1 over x plus 4, and I'm getting that again from up here where I factored and those guys canceled. It left me with just the 2 and these guys. If I wanted to know what the answer was, I would now take this 2/3 and plug it in. So I'm going to do that off to the side. I know that I'm just asking for the limits, but this will help me describe what we might, how you might see it on the test. All right, so that's 2 times 4/3 plus 1, so 4/3 is going to be plus 1 is 7/3, and then this would be 12/3 plus 2 is 14/3. Oh, that's 14/3 over, so it's 1. The limit as x approaches 2/3 from the right. So on a test, I might say, given the limits below, and I would have just these 2 limits. Given the limits below, tell me what you know about the graph of f of x. And you would say there's a hole at 2/3, 1. If you approach a number from the left or the right and it gives you a numeric answer and we're looking at a rational function, then what you're discovering is that there is a hole. And that only happens if something canceled. So a rational function where something cancels and you plug the number of that 0, right? You plug that 0 into the limit and evaluate whatever your corresponding answer is, that is the where the hole occurs, the y value for where the hole occurs. Here, state the limits required to find the horizontal asymptotes of the graph. It's just the limit as x approaches negative infinity. And the limit as you approach positive infinity. Now, I'm not asking you to work this out. I just said state the limits, but you already know that this stuff cancels. If you were to continue on with this to actually show the work, you would divide everything by the biggest variable in the denominator. This goes to 0, this goes to 0. 4 divided by 1 is 4. You would do the same thing here. Since you've already done all the work, you can just go ahead and write this. That goes to 0, that goes to 0, and you get 4. And so we do have a horizontal asymptote of y equals 4. Again, if I just asked you to state the limits, then we're really looking for like that stuff. Okay. Generally, I will have all the limits done. I'll have everything done for you. What I usually do, the way I usually answer or ask this problem is I actually have all of this. All of this. Like I will have every bit of that written out and say, what does that tell me? And you would say, oh, well that, because this is a limit at negative infinity and we get a numerical answer, that tells me I have a horizontal asymptote of y equals 4. So I would give you every bit of this work completely done, and this is what you would respond with.